Hey there, AP Pre-Calc. Let's look at Lesson 3, Day 1. We're going to talk about sine and cosine function values. Last lesson we looked at angles on the unit circle and we related trig functions of sine, cosine, and tangent. But today we're going to explore an approach to find exact values of trig functions when the point on the terminal side of an angle is beyond the unit circle with radius 1. Looking at example 1, we have the terminal side of angle theta contains the point -5, 3. And we want to find exact values of sine and cosine functions of theta. We want to use radicals if necessary and not decimals. The first thing I want to do is think about drawing a perpendicular back to the x-axis. A common mistake is students sometimes draw that perpendicular over to the y-axis. That won't work. It always has to go back to the x-axis. Then we're looking at the angle that we're calling theta prime. That's this angle right here. And we know that the leg on the x-axis has moved 5 units left, so that's -5 units long. And the leg that's the perpendicular has moved 3 units up on the y-axis. So our job is to find the length of the hypotenuse, and we can use the Pythagorean theorem where x squared plus y squared is the radius squared. Remember, we're thinking of this as the end point on some large circle coming across here. So if x is -5 and y is +3, then squaring both of those terms, we have 25 plus 9 for our r squared value, and that gives us an r value by taking the square root of both sides as the square root of 34. So we know the length of the hypotenuse. Now to translate that into our trig language, we want the sine of theta. So the sine of theta is the length of the side opposite, which is 3, and the length of the hypotenuse, which is square root of 34. And then to find the cosine of our angle theta, that is the length of the adjacent side divided by the length of the hypotenuse. So we're using those Pythagorean theorem ratios in that right triangle we created. In example 2, let's let theta be an acute angle such that the sine is 5/6. We can draw that in quadrant 1. So I want to make an angle where we have the right ratios here. So this is our right angle. This is our angle theta. And sine is the opposite side divided by the hypotenuse. So the opposite of theta is length 5 and the hypotenuse is 6. And using the Pythagorean theorem again, our length for x plus the length for y is going to be the radius squared. So x squared plus 25 is equal to 36, and x squared is 11. So 36 minus 25. So the square root of 11 is the length on the x-axis. This is length square root of 11. This is my x and this is my y. Evaluate the cosine and the tangent for our angle theta. Cosine, we said, is the adjacent side, adjacent to theta. So adjacent to theta is radical 11, and the length of the hypotenuse is 6. And tangent is the opposite side length divided by the adjacent. So 5 divided by square root of 11. Moving on, in example 3, if theta terminates in quadrant 3 and tangent is 4/7, find the exact values, no decimals, for sine and cosine of theta. Again, we're going to draw our angle in quadrant 3, so that's down here. We're going to drop the perpendicular back to the x-axis. to create that right triangle. And to move left, tangent is opposite. Let's think about this now. Tangent of an angle is the opposite side divided by the adjacent side. So opposite is 4 and adjacent is 7, but danger beware because we have moved left and down to end up here. So you need to think about the sign of the movement, and I mean S-I-G-N, not S-I-N-E. Looking for the length of the hypotenuse, we need Pythagorean theorem, so -7 squared plus -4 squared is the radius squared. That's 49 plus 16 is the radius squared. So 49 and 16 is 65, and if we take the square root of both sides, we have the length of the hypotenuse, radical 65. Then we want the sine. So the sine of our angle theta is the side opposite divided by the hypotenuse, and the cosine of theta is the side adjacent divided by the hypotenuse. Now, I had said earlier in our course we won't be using degree measure, we'll be using radian measure throughout the course. But if you're familiar with the 30, 60, 90 degree triangle and the 45, 45, 90 degree triangle, we want to use that as a learning tool as we look at these two famous triangles. You might recall from geometry that the shorter leg on the 30, 60, 90 is half the hypotenuse of an equilateral triangle. So that gives us this side is 1 and this side is 2. So these angles are both 60 degrees. These are both 30 degrees. And in the isosceles right triangle, both legs are equal, so we have two 45-degree angles. For example 4, I want to complete the table using the two triangles. So the sine of 30 degrees will be equivalent to the sine of pi over 6 radian. So sine is opposite divided by hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Those are for the 30 degrees. The sine of 45 degrees is opposite divided by hypotenuse. Cosine of 45 degrees is also adjacent divided by hypotenuse, and tangent is opposite over adjacent. Then finally, the sine of 60 degrees is the opposite side divided by the hypotenuse. The cosine of 60 is adjacent over hypotenuse, and tangent is opposite over adjacent. Adjacent is 1, so we'll just leave that as radical 3. Now, what do you notice about the complementary angles? Do you see that the sine of 30 and the cosine of 60 are the same values? They're both 1/2. And the sine of 45 along with the cosine of 45 degrees are both radical 2 divided by 2. The sine and the cosine and its complement, cosine, are equal. The sine of an acute angle is equal to the cosine of that angle's complement. And remember that complementary angles sum to 90 degrees. I will see you tomorrow for day 2 of this lesson.